Okay guys, we're back here on our second part of our precision measurement lesson here. The whole idea is, we need to be practicing for the NIMS CNC operator certification exam, studying the Cengage material that we have available. Okay, and where we left off was the vernier measuring tools here. So I wanted to bring you guys back and review just a couple things quickly. If we take a look, we've got the main scale of the vernier caliper, and then we also have the vernier scale on the sliding jaw. So essentially what we're looking for is everything before the 0 on the vernier scale. So if we take a look at this example, we see that we have 0 down here, and we have 1 whole inch showing. Okay, and it looks to me like there's about 25 thousandths. So each of those individual lines between 1 whole inch and 100 thousandths of an inch is 25 thousandths. So it looks like we have 1 inch 25 thousandths. And then we're going to go down to the vernier scale, and this is where it gets tricky in that we need to find the line that lines up with a line on the main scale. In this case, we have the 15 thousandths line lines up the best. Okay, and what we'll do is we add all those numbers together, and we end up with our final measurement. Okay, we're going to skip ahead here just a little bit to micrometers. So taking a look at a micrometer, the different parts, we've got the frame, the anvil, the spindle, which is the moving part that's going to be moving in and out, the sleeve or barrel, which is the fixed part, and we have our thimble, which is going to be traversing across the barrel. We have several different sizes of micrometers, everything from 0 to 1 inch, all the way up to 6 to 12 inches. Now, taking a look at how we measure with a micrometer, what we're going to do first is find everything before that edge of the thimble. Okay, that leading edge of the thimble, we're going to take a look at all the numbers that occur before that. So in this case, it appears that we have 0, 1, 200 thousandths showing on the barrel. And then we're going to go down similarly as we looked at the vernier scale. We have 25 thousandths increments. So it looks like we have 25, 50, 75 thousandths showing before the thimble. So we have 275 thousandths so far. And then the next thing that we're going to do is take a look at the thimble and find the line on the thimble that best lines up with the center line on the barrel. In this case, it looks to be about 10 thousandths. So we have 285 thousandths. Now, in this case, on this micrometer, on this example, we also have a vernier scale that is up above that main scale. And in this case, we have 8 ten-thousandths showing. So we have 285 and 8 tenths as our measurement. Moving ahead, different types of micrometers. And moving to dial calipers. Okay, so we took a look at the vernier scale. Now we have dial calipers. So again, we're going to be looking for everything that occurs before the sliding jaw of the caliper. So if we take a look at this example down here, example C, we have 1 whole inch showing. We have 1, 2, 3, 400 thousandths showing before the edge of the sliding jaw. And then we're going to go look at the dial. We're going to take a look at how many 1,000ths of an inch increments are showing being represented on the needle. So we have 1 inch, 400 thousandths, and then if you look at the dial, we have about 40 thousandths. So we have 1.44 or 1 inch, 440 thousandths. Digital calipers, pretty straightforward and easy. The nice thing about digital is you can swap back and forth between inches and millimeters, and they're obviously much quicker to measure with. Dial and digital height gauges, depth gauges. Then we have some transfer tools, some precision transfer tools. Now, the advantage of these is that we can get to different features that a micrometer or a caliper can't, but they do not have graduated scales on them, so they're just a transfer or a reference tool. So if we take a look at a couple different types here, we have full ball and half ball style gauges. These are for measuring hole diameters. We also have telescoping gauges, which most of you should be familiar with. Now, the process of measuring with a telescoping gauge is pretty straightforward. We're going to insert the telescoping gauge into the hole at a slight angle with the thumb screw slightly tight. We're going to rotate that handle downward, collapsing the gauge in on itself. We're going to tighten the gauge, the thumb screw of the gauge completely, and then rotate the telescoping gauge and pull it out and measure that gauge, that telescoping gauge, with a micrometer. Now, take note of how this person is holding on to the micrometer and the telescoping gauge. You gotta have a little bit of dexterity here, but holding the micrometer and the telescoping gauge in this manner allows you to move the thimble, hold on to the telescoping gauge, and hold on to the frame of the micrometer. Moving ahead here, we have dial and digital indicators coming in two different styles, with a plunge style and a test indicator. Just like dial calipers, a dial indicator is going to have this dial face, typically in graduations of 5/10. Digital indicators with a digital readout. Note in this diagram the correct way to set up a test indicator. Note that we have a little bit of preload on the end of the indicator, putting a little bit of pressure on that needle so it's not perfectly vertical. We can use dial indicators as a reference. So in picture A, we're using a gauge block stack up to zero out the indicator, and then we can slide our part underneath to see how far out of spec that part might be. Again, using dial indicators, showing how we can use them to test perpendicularity and parallelism. Sine tools are pretty interesting. A sine bar allows us to get essentially limitless angles that we can use to reference our part against the surface plate. So what you'll note is that we have a gauge block setup, a gauge block stack, and there is a known distance of the length of the sine bar, and the gauge block stack is also a known distance. So setting those two lengths, we can get the desired angle that we're looking for. Sine bars and sine blocks. A sine block obviously just a little bit wider, accommodates for a little wider part. Same thing with a sign plate and a sign vise. As you can see, we have a part that has an angle on it. We can match that angle with the sign plate or the sign bar and run an indicator across the top, making sure that that surface is parallel with the surface plate and confirming whether that part is within tolerance or not. Surface finish, essentially the average of the peaks and valleys left by a machining operation, typically measured in RA. We can measure them either with a comparator or a profilometer. We'll see examples of both in just a second. We can see that roughness is a little bit shorter of a distance versus waviness, which is a little longer surface area. Again, RA, surface finish, is just the average surface height above the mean line over a given length. So we're just taking the average, essentially, of the peaks and valleys. Here's a diagram showing some different RA finishes that we might be able to get from different machining and manufacturing operations. And here are some different surface finishes, surface patterns that may be achieved by different machining operations as well. What you might find on a technical drawing at a manufacturing facility or a machine shop is this symbol accompanied with a number call out for RA surface finish. Here you can see a surface finish comparator. It just gives us a rough idea of what different machining operations produce in the patterns that they produce and the RA finishes that are accompanied with those patterns. It's just a comparison. We can take our part and compare it to it. What is more beneficial is using a profilometer, which is a digital readout device that will take the average surface height of those peaks and valleys and give us an RA finish on the digital display. Another type of optical comparator for measuring different features of a part. Essentially, it's going to be just a big magnifying glass or microscope that's going to have, it's going to lay the shadow of our part, and we're going to be able to measure from point to point with a precision measuring device on that optical comparator to tell the distances and angles of different features of our part. And possibly the most accurate machine for precision measurement is a CMM, or a coordinate measuring machine. It's a pre-programmed, essentially a CNC machine with a probe on the end of it, on the end of the spindle, and we pre-program it to pick up on certain points of a machine part to measure that item, and it'll give us some data output that will tell us whether our part is within tolerance or not. Okay, so that's essentially it for part 2 of our precision measurement lesson. Remember, I will post a question to Google Classroom. Please write your response in the comment section of Classroom, and we'll catch you later, guys.